Hello everybody, my name is Stav. This talk is about transformers in natural language processing and a Python package called SpaCy. So we are going to see a transformer model that can perform multiple NLP tasks. We're going to use SpaCy to implement that. It should be fairly simple and it should all come together. So let's get started. My name is Stav. I was here on PyCon last year talking about topic models, but this was on Zoom. So it's really great to see people in person. I work as an NLP research engineer. I completed my master degree focusing on NLP and language models. And I recently joined the NLP IL community on Facebook. You should check it out. So mainly, but not exclusively, NLP geek. This is the plan for today. I'm going to start with transformers. Then we'll continue with multitask learning. After that, we will introduce SpaCy, and we will end with a more practical viewpoint of how to implement that. So transformers. Okay, so let's take a step back. The universe was created quite a while ago. Then starting in the 40s with neural networks, and then came the ability to scale them. So we saw the rebranding of neural networks under the term deep learning, and it improved over time, evolving to recurrent models, so RNNs and LSTM. And then came 2018, and this was the year of NLP. So a lot of interesting breakthroughs in the ability to understand language. We have the attention mechanism, we have transformers that are basically attention on steroids, and Google's BERT was released. So I'm sure you're all familiar with those terms, but just as a refresher, BERT stands for bidirectional encoder representation from transformers. So it is a bidirectional model compared to the unidirectional models that were trained before. And really, in a sense, it's a complex attention architecture that performs language modeling. So BERT was very successful, and it is inspired a lot of variants. So to name some of the popular relatives in the family, we have Roberta. Roberta is a robustly optimized BERT, and they basically showed that BERT is undertrained. So they took the same data, trained for more epochs, and achieved better results. So pretty straightforward. We also have Albert. It's a light BERT. Here we have some cool innovations actually. So the main idea is massive parameter sharing that should help with overfitting. And also we have DistillBERT. It's based on knowledge distillation, the idea of compressing a large model to a smaller one. And we use these models all the time, so they work incredibly well. And the hypothesis of why it works so well, this is due to language modeling, the task of predicting the next word. So for example, if I have the sentence, Bar-Ilan University is located in, and we want to give different probabilities to different words here. So this is kind of like the ultimate NLP task, right? Because when we are learning language models, we're learning many million of latent features, and these really the same features we'll need for other NLP tasks. So basically, if we have a very good language model, we can probably also build a very good name entity recognition system that finds the entities in the text. And the language model can also be used to build a named entity linking system that assigns the entities to a unique object. And it goes on for other tasks. So using a language model can also perform relation extraction, detecting the semantic relation between entities. And all of these tasks that we just mentioned, you kind of first have to construct it as a language model, and then you can build these systems. So this is what we usually do in industry applications. So if I want to build, for example, a named entity recognition system, then we don't train language models from scratch because it's expensive. So we usually take Bert or one of his friends, use it as the initialization for the encoder. We add some task-specific layers, and then we fine-tune this model with probably smaller data set that we have. And for other tasks, it works pretty much the same. So again, the weights from any transformer, BERT, for example, are used for the encoder. We add some layers and fine-tune. And in this approach here, so each model performs a single task. So this is single task learning. And the idea that we want to talk about next is how can we unify those models into a single model. This is multitask learning. Okay, so again, in the single task scenario, then we have here a model for each task. And the question is, do we really need to train 3 separate models? Because these tasks, they are different, but they're kind of related in a sense that all of them revolve some understanding of the entities in the text. So maybe we can share some information between the models. And in a model perspective, one way to achieve that is simply to remove the individual encoders from each model and replace it with a shared encoder, followed by multiple heads for the different tasks. And then we have the model learn those tasks simultaneously. So this is multitask learning. And it should be more efficient, right? Because we have less parameters to train, only one encoder. And also in inference time, so the input text here, it goes through the encoder only once. So also less computations in inference time. But efficiency is not the only motivation. So learning multiple tasks together, they can kind of reinforce each other. So it can help us with learning better representations. Basically generalization. So these are the 2 benefits of multitask learning, efficiency and generalization. But it's not guaranteed. So the idea of multitask learning, it sounds intuitive and promising, but it doesn't always work well. And the reason is that we have a critical assumption here that the tasks that we are trying to learn across, that they share some structure. Now, if these tasks, they don't share any structure, then we're probably better off using single task learning. So it's something that you probably want to examine in your use case and in your domain. There's a paper that gives some good insights about which tasks should be learned together. So if you're using that, you probably want to explore that further. And now let's move on to SpaCy, and let's start with the basics, the fundamentals. To summarize in one slide, what is SpaCy? So it's an open source library for NLP in Python. It allows us to do powerful things pretty easily. The main concept is the language processing pipelines that we're going to talk about next. Why SpaCy? So it comes in with many built-in models and components that you can use out of the box, and you can also create models and train them pretty easily. And it's also important to understand what SpaCy isn't. So it's not an API, it's not software as a service, and it's also not meant for pure research purposes. It's meant for production environments. And now for the exciting part. So what's new in version 3? Okay, so version 3 expanded the command line interface that we're going to use. It introduced a new configuration system and added the support of transformers. Okay, so in the SpaCy framework, there's a main object called language processing pipeline. It looks like that, and basically it's a sequence of components or pipes, and each component here refers to an actual model that performs some text processing task. So given the input text, it goes through the pipeline by order, and each component adds its annotations to the text. The output is a doc object with the annotations from all the components. Now, in the new version, you can now plug in a transformer component to the pipeline. So here you can use any transformer that you know and love from any framework. So you can use Hugging Face. And you probably want to use a GPU to train a transformer-based pipeline, but later you can deploy them on CPU. Okay, so SpaCy supports a range of built-in components. To list some of them, you can see this list. So these are the actual Python objects of pre-trained models that you can use. And you can initialize them simply by using these names, and SpaCy will know how to create them. And there are many other built-in components, so you can just check the documentation of SpaCy. And another cool idea is custom components. So in addition to the list here that we just mentioned, you can also create a component for your own use case. So a component, basically, it's a function or a callable that receives the doc object, modifies it, adds some annotations, and returns the doc object. So for example, relation extraction is not a built-in SpaCy component. So if you want to use it, you need to build a machine learning model that takes in the document as the input, predicts the relations between the entities, and returns a doc object with these predictions. Okay, so now let's say that we use SpaCy, we want to build a language processing pipeline that contains entity recognition, linking, and relation extraction. So as we already understand, entity recognition and linking, we can use the existing model. These are built-in components that we can just further train. But for relation extraction, we have to create the model. So let's assume, just to simplify things, that we have such model. In the links in the last slide, then you can find the implementation. But let's say we want to train this pipeline. So if we want to perform single task learning to train it, then we'll have to plug in a transformer layer for each one of the components here. So we have independent embedding layers. Now, if we want to train the same pipeline, but we want to perform multitask learning, so now we have to plug in only one transformer that serves as a shared embedding layer to the other components. And the underlying mechanism in SpaCy is the transformer listener. It is basically the way these components can connect to the transformer, but we only have one transformer. And there are different trade-offs to choosing each approach. So the independent embedding layer or single task learning, we have a larger and slower model, right? Because we have several transformers, and transformers have lots of parameters. But it is more modular because each of the models here is independent of the others. So you can train one of them in isolation. And for the shared embedding layer or multitask learning, it's pretty much the opposite. So we have a smaller and faster model, right? Only one transformer, but it is less composable because all of the components, they share the weights of the transformer, so they are kind of coupled. And also we know that multitask learning is not always suitable for our use case. So these are the things to consider when we choose how we want to train Python. And now for the second main element in SpaCy that we are going to cover today. This is the configuration system. So up until now, if you want to train a SpaCy model, you would be writing a training loop that looks something like that. So for each epoch, for each batch, and so on. And it works pretty well until you start to handle multiple NLP projects. And then you find yourself rewriting this code over and over again with some modifications. Becomes harder to track. So instead now, you don't need to write training loops at all. So if you use the configuration system, Now there is one single file with all configuration information. So here you can specify the structure of the pipeline, the different components. You can express here if you want to use shared or independent embedding layers. Basically configure everything, all the parameters, and no hidden values. So this is like a complete manifest of the training procedure. And it should be easier to track and document the training process. And also, if you use the exact same config file, you should be able to reproduce the exact same results. Okay, so now that we have the key concepts in mind, so we have the language processing pipeline and the configuration system, let's put it all together and see how we can use it in practice. Wait for it. Okay. So we want to build an NLP system that tags the entities in the text and later assign them with unique identities. We of course use SpaCy, so we want to build a language processing pipeline that consists of two components. So we'll need an entity recognizer and entity linker. And let's say that we want to perform a multitask learning. So we add one transformer component that powers both the recognizer and the linker together. So we want to define this pipeline and then train it on our dataset. So this is what we are going to do. First we have to convert our dataset to the SpaCy format. And then we need to generate a configuration file for the pipeline. And then we have to train the pipeline and create the model. So let's start with step 1. Here we use SpaCy convert. We pass in the path of our existing dataset. We specify the output format, target output format, and it generates a file in SpaCy's binary training data format. And this file should be smaller than the original file because SpaCy implemented a very efficient serialization mechanism. The next thing we want to do is generate the configuration file for this pipeline. So here we use init-config. We specify the components that we want to include in the pipeline. So it generates a file that looks something like that. This is the config file. And we have a section for the data files and also subsections for each one of the components. And it's also important to notice here that under the entity recognizer and the entity linker, the embedding architecture is specified to be transformer listener. So this is the indication that we have a shared embedding layer because we use here the transformer listener and not an actual separate transformer. And you can also choose the optimization metric. So here it is set for higher accuracy, but you can also optimize for efficiency in terms of memory consumption and inference time. So this is another thing to explore. And finally, we want to kick off the training process. Simply use SpaCy train, pass in the config that we just generated. And if we have some customized components like a relation extraction that is not built in SpaCy, so this is the way to pass in and register these components. The output looks something like that, and eventually it creates the model that we can later load and use in runtime. So a quick recap of this process. We started with SpaCy convert to create the data. Then we used init-config to generate the configuration file for the pipeline. And then SpaCy train, using the configuration file, generates a model. All we have to do next is SpaCy load and pass in documents that we want to predict the different tasks for. That's it. Let's do a quick summary. Okay, we started with transformers. We talked about BERT and the different relatives. We talked about fine-tuning. Then we moved on to multitask learning. versus single task learning, the concept of independent and shared embedding layers, the different trade-offs. We moved on to SpaCy. We talked about language processing pipelines, about built-in and customized components, and the configuration system. And lastly, we saw a use case of how we can use the command line interface and create a pipeline, train it, and get a model that we can use. So these are the materials I've used. Here you can find an implementation, for example, for relation extraction components, and some links about multitask learning, and the main source here is the SpaCy documentation that you probably want to check later. Thank you for listening. Have a wonderful weekend.